Lesson 2 in the trigonometry unit is on special right triangles, which you may have seen in grade 10, but we're going to review them quickly. Last lesson, I said that one of the nice things about trigonometry is you have to use a calculator. And for every right triangle, other than the two we're going to look at, you actually do. But these two right triangles are really nice in that the answers to trig problems are, we can generate an exact value. So from last day, I want you to think about, where did you see right triangles? I thought we were talking about trigonometry angles from 0 to 360, but remember when we made a reference triangle, we automatically made an acute triangle, and when we imagined a vertical line down to the x-axis, that's a right triangle. So we're going to look at two, and the first one is a 45, 45, 90. So here's our 45 and 45, and this is an isosceles triangle. And in an isosceles triangle, we know that both those sides are equal. And if we looked at the simplest isosceles triangle, say a triangle where the sides are just 1 and 1, we could go ahead and use Pythagoras, and we could find that the hypotenuse is going to be the square root of 2. Now remember, the square root of 2 is an irrational number. It goes on forever, but if we leave it as the square root of 2, it's not a bad number at all. So there's our first special triangle, a 45, 45, 90. Our other special triangle is a 30, 60, 90. And these are the exact same triangle, except they're in the two orientations. The first orientation, the 30-degree, is on the horizontal, and the second one is the 60 degrees on the horizontal, but they're the same. And if you remember back to grade 10, there was a really nice sine ratio that gave us a nice answer. Again, if you did the sine of 35 degrees, it would be a horrible, horrible decimal number. But if you press the sine of 30, you get 0.5, 1 over 2. And remember what the sine ratio is. It is the ratio of the side opposite the angle compared to the hypotenuse. So by simply knowing the sine ratio of 30 degrees is 0.5 or 1/2, then we get this exact value. And then when we go ahead and we use Pythagoras, well, the other side will be this root 3. Now again, root 3 is a irrational number. It goes on forever, but when you leave it as root 3, it's nice. So as you move forward in your trigonometry, we're gonna get away from our calculator, and we're gonna look at trigonometry where we can find an exact value. So before we go any further, let's take a look at the following example. A little bit of review from last day. We want to look at theta equals 135 degrees. And remember how we determined our angle in standard positioning. We start on the x-axis and we go through 135 degrees. So here would be our theta of 135 degrees. And again, it doesn't have to be a perfect picture. It just has to kind of look nice. And there's our angle, and it's in the second quadrant. Now, the first question I want us to remember is how to find a reference angle. And a reference angle is the angle formed between the x-axis and the terminal arm. And there it is right there. And we had a little formula from last day, which you don't have to know, but theta r is equal to 180 minus theta. And in this case, our reference angle is going to be 45 degrees, which is really nice because we're going to use it. So the next thing I want us to be able to do is, as we did last class, is to make this reference angle in the three other quadrants. So part C is determine the measure of three other angles in standard position that have a reference angle of 45 degrees. So I'm just going to do these as dashed lines. So if our reference angle is 45 degrees, well, in the first quadrant, here would be right here. This would be our theta r. So in quadrant number 1, I'm just going to label it like this. Theta, again, our angle in standard positioning, in quadrant number 1 would equal 45 degrees. So the reference angle equals the angle in standard positioning, and that's what we saw last day. If we look at quadrant 3, again, we have the same reference angle. Again, I'm not going to highlight it, but that's what I mean right there. Well, in the third quadrant, the theta is equal to 180 plus 45, which is 225. And in theta 4, or sorry, the angle in standard positioning in quadrant 4, again, this would be our reference angle of 45 degrees. And this angle, theta, remember, all the way around from the x-axis into the fourth quadrant would be 360 minus 45, which would be 315. And of course, theta in quadrant 2 is 135 degrees. So the nice thing about identifying a reference angle is we actually make a grade 10 acute triangle. And we're going to see that if we can make an acute triangle, then we can answer a bunch of questions. So these grade 10 formulas, sine, cosine, tangent, SOHCAHTOA, if that's how you want to think about it, then what we can do is we can use our grade 10 math to help us in grade 11. And that's going to be the idea in grade 12 as well. So part D, let me just add part D to our notes. Okay, now I'm just going to pick the sine. It doesn't matter what I choose. I want to know the sine of 135 degrees. In order to find the sine of 135 degrees, we're not going to worry about the 135 degrees. What we're going to worry about is our reference angle, which we're going to use to make an acute triangle. And if we have a 45-degree angle right here, because that's our reference angle that we know right here, and if I also know that this is a 45, then the other thing I know that this is a 1, 1, root 2 triangle. And the only thing I want to add to our picture is we're plotting this on a coordinate grid. So this is the negative x direction. And we're going to talk about another way to get around positives and negatives in a little bit. But for right now, in order to figure out the sine of 135 degrees, I just have to actually use my theta r and do our grade 10 trigonometry with that, and that will answer the question for the sine of 135 degrees. So let's go ahead and just look at our picture up here, and we want to know what is the sine of 135 degrees, and we're going to use this, and basically I'm going to ask this question. We're going to change this slightly. What is the sine of theta r? And theta r is 45. And if we went ahead and did that, well, the sine ratio is opposite to hypotenuse. So it is positive 1 over the square root of 2. And usually we don't want to have a radical in the denominator. So if we want to rationalize the denominator just means no radical in the denominator. So we just have to remember the fact that if we simply multiply by whatever's in the radical, we can get rid of the radical, because the square root of root 2 times the square root of root 2 is the square root of root 4. So let me just do that step. That's the square root of root 4. And the square root of 4 is simply 2. So this is called rationalizing the denominator. And we're going to do that later on in the year. But here's just something right now. Now, I would be okay. I would be okay if you left it as 1 over root 2. But by convention, we want to get rid of the radicals in the denominator. And you simply multiply it by itself, and they go away. So this might be, I just want to construct a quick little table based on these exact values. And this might be something that you're going to do a lot, and hopefully you're going to see a lot. And we're going to use this information to go ahead and solve some problems. Remember, the example we just did, this one right here, we're going to come back to this one. This is not such a worry today. We're going to talk about that into the future. But if you got out your calculator right now, I don't have mine ready to go, but if you punched in the sine of 135, enter, you're going to get a decimal. And if you punch that in, you're going to find out the answer to the sine of 135 is equal to the square root of 2 over 2, which is around 0.35. Okay, so again, a really valuable thing is to have these pictures. And we're going to have 1, 2, root 3. When we have a 45, 45, 90, we're going to have 1, 1, square root of 2. And when we have a 60 in there and a 30 up there, we're going to have our 1, 2, root 3. So let's just fill in this table. A quick little reminder of grade 10 math. With the sine of 30 degrees is equal to the opposite over the hypotenuse, so that's 1 over 2. The cosine of 30 degrees is equal to the adjacent over hypotenuse, and that's that. And again, we can't take the square root of 3. It's not a nice number, and we don't want it anyway. The tangent is equal to the opposite over the adjacent. So in this one right here, it's 1 over root 3. But if we multiply root 3 top and bottom, 1 times root 3 is 3. Root 3 times root 3 is the square root of 9, which is 3. So here are our nice values. And this isn't something that's nice to have beside you as you're going through your homework and you're doing some practice problems. So you don't have to worry about them too much. Okay, let's look at 45 degrees. Well, the sine is the opposite, which is 1 over the square root of 2. And again, multiplying top and bottom by root 2 gives us that. The cosine is the adjacent over the square root of 2, which is the same as above. And the tangent is equal to the opposite over the adjacent, which is 1 over 1. So here's our opposite, here's our adjacent, and that's just 1. That's the way you check your calculator, by the way. Make sure your calculator's in degree mode. Press tangent of 45, and it has to equal 1. And if it doesn't, seek help. Okay, so I'm just going to fill these in. 60 degrees opposite over hypotenuse. Cosine of 60 is adjacent, which is 1 over hypotenuse, which is 2. And finally, the tangent is opposite, which is root 3. And adjacent is 1, so I'm just going to write root 3. So here's what we want to be able to do. We want to be able to use these basic acute triangles, these special acute triangles, to go ahead and solve problems. Now, a really good thing to do whenever you have one of these special triangles, regardless of the numbers of the original, is to put in your numbers. So I'm going to put them, and I'm going to circle them. So if here's my 30 up here, I know that the sine of 30 is 1 over 2. So in this triangle, the hypotenuse is always 2, and the side opposite 30 is 1, and the side opposite 60 is this. So in solving this particular triangle, we could punch in the cosine of 60 is, or the sine of 60 is equal to x over 12, and we could do a manipulation, and if we did that on our calculator would give us a decimal, but that's not what we want. We want an exact value. So in this question right here, we could set up a ratio, And instead of pushing buttons on our calculator, we could go ahead and substitute the exact value, these things that we have up here in the table. So if I were going to figure out x, I would use the sine ratio. So the sine of 60 is equal to x over 12. Now remember, we're trying to solve for 12. What's another way of writing the sine of 60 degrees? Well, given that it's a special triangle, all special triangles, the sides are in these proportions. So the basic special triangle we looked at was a 1, 2, root 3 triangle. And if you look at this one, there's a definite connection. There's a really nice connection. So basically, if I said, how much bigger is this triangle than the triangle we have? And you would say 6 times bigger, because our basic one has a hypotenuse of 2, and this one has a hypotenuse of 12, and 12 is 6 times bigger than 2. And given that these are all proportional, these triangles are all 30, 60, 90, they always have this base relationship, then every side of this triangle has to be 6 times bigger than what we started off with. So that's one way you could go ahead and do it. So you could know using that logic that what the answers would be, but we're going to set up a proportion. We're going to use our proportional ratios. So the sine of 60 is equal to root 3 over 2, and that's what we have in our little table right here. This would be our base ratio, the exact value of the sine of 60. And we're just going to enter that in. So the sine of 60 is equal to that. And the sine ratio in this triangle is equal to x over 12, opposite over hypotenuse. And what we're simply going to use is we're going to use an exact value instead of our calculator, and we're going to go ahead and solve this. So the way we would solve it is we'd multiply both sides by 12 to isolate x, and we get 12 root 3 over 2, which is 6 root 3. And again, if you use this times 6 ratio right here, well, this also has to be a times 6 ratio, and that's what I mean by there's more than one way to solve it, but we're looking at this exact value. So if we go ahead and solve for y in using our exact values, then if I were going to solve for y on my calculator, I'd say the cosine of y, or sorry, the cosine of 60 is equal to adjacent over hypotenuse, and I'd multiply both sides by 12, and I'd go 12 times cos 60, hit enter on my calculator, and my calculator would give me the answer. The answer is 6. But if we use our cosine ratio, the cosine of 60 has this base ratio, 1 over 2, right? Here's our base ratio, 1 over 2 for the cosine. And in this particular triangle, that is y over 12. And again, there's many ways to solve this problem, but if we multiply both sides by 12, 12's over here cancel out, and we end up with 6 equals y. And again, if you just do, hey, given a hypotenuse relationship is times 6, then the horizontal side has to be times 6 as well. So the key idea here is when you don't have a nice number, a nice ratio like 1 over 2, your calculator is going to give you a nasty, nasty fraction. And we have to get used to doing exact values. So let's have one last example. Find the exact area, no decimals, find the exact area of an equilateral triangle with a height of 6. So one of the strategies that you learned a long time ago is a picture is always a good thing to do. And again, it doesn't have to be a perfect picture, but here's my equilateral triangle. And there's something really important about equilateral triangles. They all have the same angles, which means they're all equal to 60 degrees. Now you're told the height of this triangle is 9. So that becomes really important because what we've just done is we've cut our equilateral triangle in half and we've made two 30, 60, 90s. And it doesn't matter which side you do because ultimately here's what I wanted in our equation. We're going to find out that here's what we need to know. We need to know the base. So again, a strategy from elementary school, draw a picture. Another strategy is, well, write down anything you know, and that's what I did on my picture. I put the height, and I want to know the area of a triangle, and there's my formula. And if you look at what you know, well, I know that because it's part of the formula. I know that because it's given right here. And in order to answer this question, again, what I want to know is I want to know the area. So in order to answer this question, I need to know the base, and that's what we have here. So given that we've cut this in half, the only thing we really have to know is I'm going to call it little a. If I could figure out what that is, then in order to figure out b, I simply multiply by 2. I double it. So the question would become, well, how can I answer this question exactly? And again, it comes down to realizing that we have a special triangle. So here's what I'm going to do. I'm going to write the picture I want. I don't need the other side. And here's what I know. So we need to figure out what little a is. And again, we have our basic ratio. We have our 1, we have our 2, and we have our root 3. And if we use this proportional reasoning, we could go ahead and solve it. But if we did our basic trig ratios, we could go ahead and solve it as well. So in this one right here, well, what do I know? I know this 9, and if we looked at this thing right here and went, okay, how much bigger is 9 than root 3? Well, we could figure that out that way too, but we could also figure out that how do I go from here to here? And if I could figure out how to go from root 3 to 1, then I could also do the same thing to go from 9 to whatever a is. So again, if you remember about your similar triangles, all sides are in the same proportion. If we can figure out how much bigger one is than the other, then we could go ahead and do it. So ideally what we're doing here is, how do I go from root 3 to 1? Well, I'm going to divide by root 3. Root 3 divided by root 3 is equal to 1. And if that's the case, we're going to have to do the same thing. So a is going to equal 9 divided by root 3. And again, if a is equal to 9 divided by root 3, then b is equal to 2 times 9 divided by root 3, which is 18 over root 3. So here's our b. And we're simply going to put that into our formula. 1/2 times 18 over root 3 times 9. And that cancels that out. And we end up with 1 times 9 times 9 is 81. And 1 times root 3 is that. And we're going to multiply both top and bottom by the square root of 3. Because we don't want a radical. And root 3 times root 3 is square root of 9. The square root of 9 is 3. And it's always a good habit to simplify as much as possible. So we looked at a few different ways of using exact values, whether it's a proportion, whether it's using a ratio, whatever we want. And ideally, what you want to do is you want to practice a few of these, practice them doing a ratio, practice them by setting up your trig ratio and putting in the appropriate values, like our table right here. That's why it's nice to have the table always handy, and figure out which way you like the best. What does your brain like the best? There's no best way, there's just a best way for you.